We previously discussed Stokes' theorem, which briefly says that integrating the curl operator over a surface is the same thing as calculating the work done by the vector field on the boundary of that surface. Now, I'd like to present our last vector calculus theorem of the semester, which is called Gauss's divergence theorem. So in Gauss's divergence theorem, the domain that we focus on is a solid domain in 3 dimensions. So here we let D be a solid domain in R3. So the figure we're looking at here is some sort of 3-dimensional blob. Well, the boundary of such a domain is notated the same way that we've been denoting boundaries. So we write partial D to refer to the boundary. And here, the boundary is the outer shell of our domain. Let's see this with an example. So let's say that D is the so-called unit ball, which is described by the rectangular equation x squared plus y squared plus z squared is less than or equal to 1. So in this region, what we're looking at is the unit sphere with everything inside filled in. So the unit sphere with everything inside filled in is what D represents in this example. Well, what is the boundary? The boundary is the outer shell of this ball, which is exactly the unit sphere. And the unit sphere is described by the equation x squared plus y squared plus z squared equals 1. So in this example, the domain in question was described by this inequality, x squared plus y squared plus z squared is less than or equal to 1, which describes this 3-dimensional solid, including the unit sphere and everything inside of it, whereas the boundary is the outer shell, which is the unit sphere itself. X squared plus y squared plus z squared equals 1. So one thing to notice about our previous example was that D represented a 3-dimensional domain, and its boundary was a 2-dimensional solid, or a 2-dimensional surface. Well, we say that a surface S is closed if it has no boundary. So here we have an example of a closed surface. Here what we're looking at is the outer shell of some 3-dimensional blob, and there is no outer edge to this surface. So we would write here that the boundary of S is equal to this symbol, which is sort of like a 0 with a strike through it. On the other hand, if we were to look at like the lower half of this surface, so if we were to just chop off the surface at the hemisphere we've sort of drawn in here, we would be working with a surface that is not closed. Here, the outer edge is sort of this top ring. So the boundary of this surface is this top, what looks like maybe like an ellipse. And we use special notation sometimes to indicate that a surface in question consists of one or more closed surfaces. We write double integral with a circle around them with a subscript of S, to indicate that the surface we're working with consists of one or more closed surfaces. So the convention that we will adopt when we discuss the divergence theorem is that the domains that we work with, D, will be domains whose boundary is a union of closed surfaces. Let's see this with an example. So in this example, we're defining a domain by an inequality, or 2 inequalities. X squared plus y squared is less than or equal to z, which in turn is less than or equal to 4. It's not terribly difficult to visualize this solid domain. If we were to look at the 2 extremes of these inequalities, the first one would be x squared plus y squared equals z, which is the standard paraboloid. On the other hand, if we didn't have an upper bound for z here, the paraboloid would extend forever. So the inequality z is less than or equal to 4 tells us when the paraboloid ends here. So what we're looking at is everything on and inside the paraboloid that's below z equals 4. So if we want to think about the boundary of this domain, the boundary of this domain will consist of 2 surfaces. There's sort of a bottom part of the outer shell and the top part of the outer shell. The bottom part here, which we're calling S sub 1, is described by the equality part of our first inequality. X squared plus y squared equals z gives us the bottom part of the boundary of this surface, and that's the part that's a paraboloid. The top part here is the second part of the boundary of this surface, or of this domain, and this is described by z equals 4, where here z equals 4 is bounded by the paraboloid. So in this situation, we would write the boundary of D is the union of S1 and S2. So the outer shell of this three-dimensional domain includes both of these surfaces. So we write boundary of D equals S1 union S2. Okay, so now that we have a notion of boundaries of solids, we can define the orientation of a boundary of a solid. So here, the location of the domain relative to the normal vector of the boundary determines the orientation of the boundary. It's actually somewhat easy to determine orientation in 3 dimensions in this way. To say that the boundary is positively oriented is to say that the normal vector always points away from the domain. So in the figure on the left here, we're looking at a sphere with everything filled in, and the boundary would be the outer shell, which is the sphere itself. In this case, we've chosen a normal vector that points away from the domain, which means that the boundary in this case is positively oriented. In the figure on the right here, we have the same domain, except we've chosen the opposite direction for our normal vector to the boundary. Here, the normal vector points into the domain, which means that the boundary is negatively oriented. So positive orientation means that the normal vector points away from the domain. Negative orientation means that the normal vector points into the domain. And just like with examples we've done before, we need to look at every part of the domain of the boundary of a domain to determine orientation. In the figure on the left here, we're looking at a domain that's in between 2 spheres. So our domain has 2 shells. There's this outer shell and an inner shell. So in this case, positive orientation means both shells have a normal vector that point away from the domain. So in this case, we need our outer shell here to have a normal vector that points out of the sphere. And since the domain is between this outer sphere and this inner sphere, the inner sphere needs to have a normal vector that points into itself, because the domain here is in between the 2 spheres. In the figure on the right, for negative orientation, we need the opposite. The domain is still the domain between these 2 spheres. So here we have a large sphere where we've sort of hollowed out the center. And to have the negative orientation means that both shells have normal vectors that point into the domain. So for the outer shell here, we need the normal vector to point into the sphere. And for the inner shell, we need the normal vector to point out of the sphere, that is, into the domain. So the convention that we adopt in the divergence theorem is the same convention we've adopted all along. Unless we state otherwise, we always assume that the boundary of our domain is positively oriented. So here we have an example to illustrate how we can do boundary surface arithmetic when we assume the positive orientation. Here, we're looking at a domain that is the inside of this large ellipsoid and outside of these 2 spheres inside of this larger ellipsoid. So to have the positive orientation, we need the normal vector for this outer surface S1 to point away from the domain. But in our presentation here, we've equipped S1 with a normal vector that points into the domain. For our first inside sphere here, we have a normal vector that points into the sphere, which is actually away from the domain in this problem. And for our second sphere inside of this domain, we have a normal vector that points out of the sphere, which means it's pointing into the domain. So our domain in this example consists of three surfaces, S1, S2, and S3. However, S1 and S3 carry the negative orientation because their normal vectors point into the domain, whereas S2 carries the positive orientation because its normal vector points away from the domain. So in this example, the way we would efficiently communicate this is we would write that the boundary of our domain is equal to negative S1 to indicate that S1 has a normal vector pointing into the domain, plus S2, which indicates that S2 has a normal vector pointing away from the domain, and then minus S3, which indicates that our normal vector for S3 points into the domain. So we have two negatives and a positive in this case. Okay, so in Gauss's divergence theorem, the motivation is to solve certain types of flux problems. Let's quickly remind ourselves about the concept of flux. In the concept of flux, the idea is that we're presented with a fluid flow represented as a vector field F, and typically here the units will be some sort of velocity units. In this case, we're choosing meters per second. And the idea is that this fluid flow flows through a surface S. So here what we're representing is the data of a surface and then one point on the surface where we can measure our vector field. Well, flux, by definition, is the rate at which fluid volume flows through the surface. So the units here for flux should be volume units per time unit, which would be, in our case, meters cubed per second. So the question we'd like to present now will have context given as follows. Let's say that we have a vector field F inside of a three-dimensional domain D. So let's say the domain we're working with consists of this outside surface and everything inside of it. Well, let's say now that we have a vector field inside of this three-dimensional domain. So at every point inside of this three-dimensional domain, we have a vector prescribed by a vector field. Well, in this situation, we define the flux out of this domain as the double integral over the boundary of this three-dimensional domain of f dot with d vector s. In other words, the flux out of this domain is defined as the flux of this vector field over the boundary surface of this three-dimensional domain. Note here that we're using this double integral with the circle notation simply to indicate that the boundary of this domain consists of one or more closed surfaces. And in this particular picture, there's one part of the boundary. So how do we interpret the idea of flux out of a domain? Well, the flux out of a domain D is the rate that fluid volume either enters or exits the domain. So if we do our flux integral over the boundary of a domain and we get a negative number, the way to interpret this negative number is that the net flow is into the domain. On the other hand, if we calculate our flux integral over the boundary of our domain and we get a positive number, the way to interpret this result is that the net flow is out of the domain. And then finally, if we do our flux calculation over the boundary of our domain and we get 0, this is telling us that there is 0 net flow. So any fluid volume that is flowing out of the domain is counteracted by fluid volume elsewhere flowing into the domain. And it's also convenient to note that flux integrals respect boundary arithmetic. So actually in this slide I have a small typo, but we'll fix this together and I'll fix it in the slides. So here we have the data of our surface or our domain from 2 slides ago, and we're equipping the boundary surfaces with normal vectors. So here S1 is maybe the first boundary surface, and here its normal vector is pointing into the domain, which indicates that S1 is negatively oriented. On the other hand, we have the second boundary surface, S2, and its normal vector is pointing into the sphere, which is actually away from the domain. So S2 actually carries the positive orientation. So that's actually a typo that we'll address in a moment. And then S3 has normal vector pointing away from the sphere, which is actually into the domain, which indicates that S3 has the negative orientation. So here, our flux integral over the boundary respects the correct boundary arithmetic. Let's correct the typos together. We said that S1 has the negative orientation because its normal vector points into the domain, which indicates that we should subtract a flux integral over S1 when we do our flux calculation. We then said S2 has a normal vector pointing away from the domain, which indicates that S2 carries the positive orientation, meaning we should add the flux integral over S2 should we calculate it. And then finally, S3 has a normal vector pointing into the domain, which means S3 carries the negative orientation, which means we should subtract it when we do that flux calculation. So again, there are typos here. I should have colored N2 in green and N3 in red. And then the correct way to read this line would be that the flux over the boundary of this domain would be negative flux integral over S1 plus the flux integral over S2 minus the flux integral over S3. I'll correct that in the slides, and so you should check that when you read over your slides. So let's do an example of a flux integral out of a domain. Here we're defining a domain as 1 less than or equal to rho less than or equal to 2. And here, rho is the variable we use in spherical coordinates. So the domain we're working with here is the region outside of the sphere of radius 1 and inside of the sphere of radius 2. So we have the ball of radius 2 out here, and we've scooped out the center, which is the ball of radius 1. We're also defining the data of a vector field here. This vector field has coordinates negative 4yz, 4xz, and negative 3z. And the units here are meters per second. So let's say that we wanted to parameterize the boundary surfaces of this solid domain. Well, here there are 2 of them, and they're both spheres centered at the origin. So we can parameterize with maybe one parameterization, but we leave a variable rho to account for the 2 different surfaces. So if we parameterize either one of these surfaces, we will change the value of rho depending on which surface we're working with. And here what we're doing is we're writing down the surface in spherical coordinates. So you want to think of rho as fixed here and phi and theta as the variables. So here, x sub 1 would be setting rho equal to 1, which represents the unit sphere in the inside of this domain. And x sub 2 is what we get when we set rho equal to 2, which is the outside sphere of radius 2 for this boundary. Well, if we bother to calculate the normal vector to any one of these parameterizations, what we do is we take the partial derivative of our parameterization with respect to the first variable, which is maybe phi. Then we take a partial derivative with respect to the second variable, which is maybe theta. And then we take the cross product of those 2 tangent vectors. And here we end up with a result. Now, if we pay attention, we realize that the normal vector with this result carries an orientation. If we set rho equal to 1 and look at the direction of our normal vector, we find that it is actually pointing out of the unit sphere, which is actually into the domain. So our parameterization of the inside part of our boundary here is negatively oriented. If N2, so if we set rho equal to 2, and we look at our normal vector, we find that we're also pointing out of the sphere, which is actually away from the domain. So our parameterization of the outer shell of this domain carries the positive orientation. This will be significant in a moment when we do our flux calculation. So now, if we calculate our flux integral over either part of this boundary, so we're leaving rho as a variable here, well, how do we do this? We should, the mechanics say that we should take the dot product of our force or of our velocity flow field with our normal vector. And when I did the arithmetic here, I got -3 rho cubed times cosine squared phi times sine of phi. And then we would be doing this integral d phi d theta, where phi ranges from 0 to pi, and theta ranges from 0 to 2 pi. When I did the calculus here, I got -4 pi rho cubed, and here the units would be meters cubed per second. Those are the flux units. So now, if I want to calculate the flux of this vector field out of the domain, the correct symbol here is double integral over the boundary of our domain of f dot d vector s. And according to our two parts of our boundary, we should subtract the flux over the inner surface and add the flux over the outer surface. So we have to subtract off this first part of our flux because our choice for our normal vector for the inner boundary surface points in the wrong direction. And now all we need to do is use our formula we derived previously. So the first thing we'll do is we'll set rho equal to 1 and then negate, which would be 4 pi. Then we add whatever we get when we set rho equal to 2 and then add the result. So that'll be -4 times pi times 8. And when we do the arithmetic here, we get -28 pi meters cubed per second.